Welcome back, students. In this lecture, we are going to learn how to calculate Q, W, delta U, and delta H, our four thermodynamic properties that we've been talking about so far. Last time we learned how to calculate work, at least for a couple of examples. We learned that work is a path function, meaning it was dependent on the path taken. So we looked at three different compressions last time and noted that they all had three different values of work. So we have to know what the process is that actually occurs in order to calculate work. The same is true for heat. Delta U and delta H are not the same. All we need to know is the initial and final states. So putting these things together, we can calculate all four of these properties given a certain amount of information about the initial and final states of the system. So the learning goals for today are simply going to be how do we calculate heat, work, delta U, change in internal energy, and delta H, the change in enthalpy for systems of ideal gases. As we go through some examples, and we'll work on example problems in class, we'll go through the theory here and then go through a bunch of problems in class. We always have to remember that at this point, we are still using ideal gases. So don't forget, you can use the ideal gas law. There'll be lots of times where we have a system of gas. We know the pressure and volume and number of moles, but we're not explicitly provided with the temperature. And that's okay because we don't need to be provided with the temperature. We can figure that out using the ideal gas law. All right, now let's jump into the board here and go through some examples. Let's start by calculating the change in internal energy. We've already seen some of these calculations before. We'll say that our change in internal energy is equal to the heat at constant volume. Remember, we talked about this before. If we add heat into a system when the volume can't change, then there is no work. So we know that delta U is equal to heat plus work. If the volume is constant, the work is equal to 0, so the delta U is directly equal to the heat. That's what we mean when we say delta U is equal to QV. Now, what is the heat at constant volume? It depends on the heat capacity. So we can say that the heat at constant volume is equal to the integral of the heat capacity at constant volume, dt. And what we'll often do is use molar quantities here. So we can say then that this is equal to N CVM, where N is the number of moles, CVM is the molar heat capacity. So CV here is just the raw heat capacity of the system, and then we have dT. In most cases, and we've talked about this before, we can assume that the heat capacity is independent of temperature. That means it has no temperature dependence. It is not a function of T. So what we can do is then pull N CVM out of the integral. And delta U is equal to N CVM times the integral of dt from the initial T to the final T. And then what we end up is simply N CVM delta T. And this is an equation we can use to figure out what the change in internal energy is. Remember that this is always true. So even though we got this final equation by assuming that we had a constant volume heat, it doesn't matter whether or not our process at hand actually has a constant volume heat because these things are all state functions. So delta U is always equal to N CVM delta T. Now, this is the heat if we have a constant volume process. If we have some other process, this is not the heat, and delta U is not equal to the heat. But if it is a constant volume process, it is. So what do we need to know to figure out how the internal energy is changed? Turns out we need to know the heat capacity, which is a number that you'll either look up or be provided, and then additionally, we need to know delta T and the number of moles. So what we can do with this is if we have a delta T for a process, we have an initial temperature and a final temperature, we have the number of moles, we have the heat capacity, we can put those things together and figure out the delta U for our process. For ideal gases, we can actually have a pretty good description for our heat capacity, and we'll see some of this in the first lab, and also way later in class we'll have enough theory to go through deriving this. It turns out that the molar heat capacity at constant volume for an ideal gas is equal to 1/2 R times the number of degrees of freedom that are active. Now, we can calculate this pretty easily based on quantum mechanics. So something like helium exists as a single atom, and it has 3 translational degrees of freedom. And so the heat capacity for helium would then be 3/2 R. And if you go look up the molar heat capacity at constant volume for helium, you will find out that it is exactly 3/2 R. So it's 1.5 times R, the gas constant. Now, if we move on to something like nitrogen, what do we get? Well, here we have 3 translational degrees of freedom, and we have 2 rotational degrees of freedom, and we have 1 vibrational degrees of freedom. Now, you hopefully will remember from last semester that vibrations for small molecules are not really accessed at room temperature. And so we don't expect this vibrational degree of freedom to be accessed for nitrogen at room temperature. And so we then therefore have 5 degrees of freedom. And what kind of heat capacity we expect is a 5/2 R heat capacity. And if we measure this, if we look this value up, we find out that it is very, very close to 5/2 R. Now, it starts to be a little bit different because we do have a little bit of contribution from the vibrational degree of freedom. The actual amount of vibrational degree of freedom that gets brought in is pretty complicated, and we're going to look at this a little bit next lab and then in much more detail in the future, but we can use statistical mechanics to actually predict the heat capacity for gases that are approximately ideal. So if we get to larger molecules, so let's say we get to SO2, we now have 3 translational degrees of freedom. We have 3 rotational degrees of freedom because it is not an ideal gas. And we have 3n-6, so we have 3 vibrational degrees of freedom. And so what would our heat capacity be for SO2? Well, in this case, we have 6 degrees of freedom that we're pretty sure are relatively uniformly accessed. So we would expect maybe 3R. Then we have some extra contribution from these vibrational degrees of freedom. But it is a little bit more that shifts our heat capacity away from this 3R value. And we'll talk more about this in lab. Above here, we talked about constant volume processes, but we'll also commonly encounter constant pressure processes. And if our pressure is constant and the volume is not, our heat is not a direct measurement of delta U. Rather, delta U is now equal to heat at constant pressure plus the work that goes along with that. And now we have expansion. And what we'll say is we'll use our differentials here because we can't really have we want to figure out what these heat and work are. So we'll say that du is equal to dq plus dw. And so this expression, remember we talked about this last time, reflects that our heat and work are not state functions, do not have nice differentials. To solve for delta U, we simply need to integrate this. So if we integrate du, we integrate dp, we integrate dw, we end up with delta U is equal to the heat plus the work. Now remember that work is a path function, heat is a path function, but delta U is a state function. So how do we go about solving this problem? Well, we recognize that du here, again, is equal to our dq plus dw. Now, we know from before what our work is. So our work was equal to the integral of p external dv, and that was negative there. And so that means that our dw is equal to just negative p external dv. So we can go ahead and plug this in. Now, I'm using p external here, but remember we're considering specifically constant pressure processes. So if we have a constant pressure process, this is simply negative p dv. So I can plug that in for work, and I get that du is equal to dq minus p dv. Now, what is the heat? Before we had a nice expression that said our heat is equal to our internal energy if we have a constant volume process. Let's rearrange and figure out what our heat for a constant pressure process would be. So we'll rearrange this and get dqp is equal to du plus p dv. And now we want some nice differential that we can relate this to. If we integrate this, we'll end up getting, just like before, so we'll integrate all of our terms, we'll end up with QP is equal to delta U plus P delta V, because remember, P is constant in this process. What we can do is go through some math and maybe make these things a little bit harder for ourselves to relate this to a different function. So what we'll say is that delta U is equal to U final minus U initial. And P delta V is equal to P V final minus V initial. So I can expand this out and say that I have U final minus U initial plus PV final minus PV initial. Now from here, what I'm going to do is something that might seem a little bit strange, is I'm going to say we have a P final and a P initial. Now this is of course true in some respects, as I have a final pressure, I have initial pressure. They're both the same, but I can put this notation in if I want to. I do this because it allows me to rearrange this in the following way. So I'm going to, if I have this equation written out like this, I'm going to group all the final terms and all the initial terms. And so what I'll end up with is U final plus P final V final, and then minus U initial plus P initial V initial. And what you'll note is that I have two terms that are the same, one consisting all of final terms, one consisting all of initial terms, but they're both U plus PV. So what we do is define a new state function. We define enthalpy, and these three lines means we're defining enthalpy as this. Our enthalpy is equal to U plus PV. And if I do this, I have a U plus PV final, so this term becomes H final, and this second term becomes H initial. And what you'll note is that I end up here with a delta H. So Q at constant pressure, the heat at constant pressure, is directly related to the change in enthalpy for a process. With this, we can get an idea for why we use enthalpy so much as chemists and not internal energy. The normal chemical reactions that we do are often done under the benchtop or under a hood. And what these are taking place at is often constant pressure. Unless a huge storm passes over the lab as you're doing your experiment, the pressure is always the current atmospheric pressure of the day. And so the pressure is constant, and anything that we're doing in that reaction is measurable. The heat that we go on in these processes are measurable as the enthalpy. And we can simply say how much heat was transferred. Oh, it's 10 kilojoules in my reaction. The enthalpy is 10 kilojoules. I can't do that with the internal energy unless I have a constant volume process. And while the volume is mostly constant for the kinds of reactions we do in lab, it's not explicitly true. So if the volume is constant and the pressure is constant, then delta PV is equal to 0. And so delta U is simply equal to delta H. And that's true for many biochemical reactions that happen at constant pressure and constant volume. Some sorts of chemistry involve mostly gas chemistry. And in this case, it is possible to keep the volume constant, even though the pressure might not be constant. And those sorts of chemical reactions typically revolve around delta U rather than delta H. That's not typical for most chemists. And so as we're training you up, as you're going through high school and Gen Chem and so forth, we familiarize you with the more relatable terms of enthalpy. We can actually get a calculation on enthalpy using this equation here. So we'll note that delta H is equal to the heat at constant pressure, and we have the exact same expression for constant pressure as we did for constant volume. So our delta U that was equal to the heat at constant volume ended up being the number of moles times the constant volume heat capacity times delta T, and the same is true for enthalpy. So enthalpy is equal to N times the constant pressure heat capacity times delta T. For gases especially, the constant pressure heat capacity is not the same as the constant volume heat capacity, meaning the enthalpy is not the same as the change in internal energy. We saw this last time, but there is a relationship between the constant pressure heat capacity and the constant volume heat capacity. That relationship is that the constant pressure heat capacity is R greater than the constant volume heat capacity. And these are all in molar quantities because R is, of course, in a molar quantity. And this comes from the fact that as we heat at constant pressure, we also have to expand. So more energy needs to be input into the system to do that expansion. We can rearrange this expression here to get the following. We can get NCVM delta T and then plus NR delta T. This is assuming that the number of moles of gas are not changing. We'll look at some examples in a couple of lectures for when that is, namely when we have a chemical reaction. And of course, this is a little different. And what we see here is that our delta H is equal to NCVM delta T, which is simply delta U, plus NR delta T. This is also a direct relationship to this expression up here, where delta H would equal delta U plus delta PV. And using the ideal gas law, we can say that we have delta U plus delta nRT. If n is constant, we can then say that we have delta U plus nR delta T. So we can see that all of our different relationships here are related to each other. Here we've calculated the internal energy and we've even calculated the enthalpy, but how do we calculate the heat and the work? There's not really a way, there's not a formula to calculate the heat. What we need to do is simply calculate the work in the ways we've gone over last time, and then subtract that from the internal energy. So we know that the change in internal energy is equal to the heat plus the work. We know that the internal energy is equal to NCVM delta T. We can figure out what the work is, and then our heat will simply be delta U minus the work. And so we can say that delta U is equal to N CVM delta T minus whatever the work is. So remember that the work is different for any process. We've seen a couple examples of these. So we have our work, which is always equal to the negative integral of P external dV. If we have a constant external pressure, this integral becomes negative P external delta V because we can pull that P external out of the integral. And this would be for a irreversible compression or expansion. If we have a reversible compression or expansion, where we don't have a constant external pressure, but our external pressure is at every point equal to the system pressure P, then we end up with a different integral to solve. We did this in the last lecture, and our work is equal to negative nRT times the natural log of V final over V initial. This reversible expansion in the bottom assumed that we had a constant temperature. So this is a reversible isothermal compression or expansion. Recall, to solve this, we ended up with an integral that said our work is equal to the negative integral of nRT over V. And if T is constant, we can pull that out of the integral and it's great. Now, if T is not constant, if it's varying based on the ideal gas law, and that means it's varying as a function of V. And we cannot simply pull this out of the equation. So what do we need to know in order to figure this out if we have a non-isothermal process? What we'll need is another specific example. And what we'll typically get is a third example where we have a reversible process, but it's an adiabatic process. And if you go back a couple of lectures, you'll remember we used the word adiabatic, and adiabatic for us meant that there was no heat transfer between the system and the surroundings. So an adiabatic process has a Q equal to 0. What does that mean? Well, it means that delta U in this case is simply equal to the work. What that means for us is we can have a relationship between these two things. So delta U was equal to NCVM delta T, but in this case, we can't just say delta T, we have to leave it in the exact differentials here. So we don't have delta U, but rather we have du and d work. So we have NCVM dt is what delta U is, and then our work is equal to negative nRT over V dV. What we can do now is rearrange this to bring this t that we can't integrate based on v because we don't know what t is as a function of v, and bring it over to this side of the equation where we have a dt. We'll also cancel out both of the ends here. So what we end up with is the expression cvm over t dt is equal to negative r over v dv. We simply integrate this expression to figure out what the change in temperature is. So when we integrate this expression, we end up with the natural log again because we're integrating 1 over x times dx. Both of CVM and r are independent of the variables, so we can pull them out of the two integrals here and get CVM times the integral of dt over t is equal to negative r times the integral of dv over v. We saw these integrals are just natural logs. We get CVM natural log of t final over t initial equals minus r natural log of v final over v initial. And with this, we are almost ready to go. What we can do from this is pull this together to get a nice and compact version of this equation. So what we're going to do is note that negative r is in this relationship between the heat capacity at constant pressure and the heat capacity at constant volume. We noted up here that CPM was equal to R plus CVM. So we had the expression CPM is equal to R plus CVM. So that means that negative R is equal to CVM minus CPM. We can plug this in here, and this looks like it's more complicated, but you have to trust me that it actually ends up being a little bit less complicated here. We can plug this in for R to get that CVM times the natural log of T final over T initial is equal to CVM minus CPM times the natural log of V final over V initial. What we're then going to do is divide both sides of this equation by CVM, which gives us the natural log of T final over T initial is equal to 1 minus CPM over CVM times the natural log of V final over V initial. Now, what we'll do here is come up with this ratio, and we'll say that this ratio is gamma. So we have, we'll just give this new abbreviation here where we'll use gamma, and we'll say that gamma is equal to the ratio of the constant pressure heat capacity to the constant volume heat capacity. So for an ideal monatomic gas where CVM is 3/2 R and CPM is 1 R above that, 5/2 R, our gamma here would be 5/3. Then we'll be able to evaluate this easier because now we have two natural logs that are equal to each other. So we have the natural log of T final over T initial is equal to 1 minus gamma times the natural log of V final over V initial. Using our log properties, we can say that this is equal to the natural log of V final over V initial, where these are now raised to the 1 minus gamma. So what that will give us, we can now remove the natural log because we have the natural log of this number is equal to the natural log of this number. So these two numbers must both be the same. So we'll have T final over T initial is equal to V final over V initial raised to the 1 minus gamma. To make these things kind of nice, we want to put the finals and initials together. So we'll swap the sign on this. So all we've done is flip the term in here. We put the V initial on top, and to make that all right, we switch the sign of the exponent. So by going from 1 minus gamma to gamma minus 1, we went to, say, a positive exponent to a negative exponent, and we flipped the quotient in here. Now we can put these things together. We have the final on top and the final on the bottom. So we can say that T final, V final, gamma minus 1 is equal to T initial, V initial to the gamma minus 1. And so again, for the case of an ideal monatomic gas, our gamma is 5/3. So then gamma minus 1 would be 2/3. And if we know the initial temperature, we know the initial and final volumes, we can actually solve for the final temperature. So what kind of information do we need for any of these processes? in general, how do we solve for these expressions? Let's go and look back on the slides for a kind of consolidation of all this information. These are the kind of equations that you're going to want to familiarize yourself with, as they'll show how we calculate internal energy, enthalpy, work, and heat for a variety of different processes. And note that there are, in some cases, multiple ways to go about doing these things. If you're doing it right, you're going to get the same answer no matter which way you go. So if you use the constant pressure heat capacity to find the enthalpy, you're going to get the same answer as if you do delta U plus NR delta T, and you're going to get the same answer as if you do delta U plus delta PV. But sometimes, if you don't quite understand the problem, you can be led astray. So if you accidentally use a constant external pressure equation to solve for work for a reversible compression, you're not going to get the right answer, and everything's going to be wrong from there. So what kind of information do we actually need to know? For the internal energy, we simply need to know the change in temperature. We have to know the initial temperature and the final temperature. If we know those two things, we know the change in internal energy. This is also good for the enthalpy as well, since the enthalpy is equal to delta U plus NR delta T. So to figure out the change in internal energy and the change in enthalpy, we need to know the number of moles, and we need to know the change in temperature. This will often not be given and will have to be solved for using the ideal gas law. When you're going through these problems, never ever assume anything. If it's something that I have given you and you think you need to assume something, you either are wrong or I have not given you enough information, which is entirely possible. If you assume things, you will get the wrong answer unless you happen to assume the right thing. So never assume a process is isothermal unless the text explicitly says this process is isothermal. Don't just assume I have the same final and initial temperatures. Actually do the calculations and figure these things out for yourself. If we have an isothermal compression or expansion, delta T doesn't change, and there is no change in internal energy. There's also no change in enthalpy. For work, we have to go through and figure out what kind of process do we actually have. And when we could do this, we can boil these down to these nice formula that we don't have to go through all the math we did in the slides. We can just say, I have a constant external pressure. My work is equal to negative P external delta V. I have a reversible isothermal expansion. I need to use this equation. I have a reversible adiabatic expansion. I need to use this equation. And we can go through and solve for these things. Just like before, there's going to be a lot of ideal gas law usage going on in here. There are many cases where it might appear like you don't have enough information, but in fact you do. Using the ideal gas law, you can figure out what the pressure and the temperature and so forth are if you know the volume and the temperature or the pressure. So don't forget that you have the ideal gas law as a tool for you as well. At the end, once you've calculated internal energy, enthalpy, and work, you can also calculate the heat by simply taking delta U minus the work. As always, when going through these processes, don't forget to use the things that you know. So if you have a constant volume process, you know that there's no expansion or compression, meaning there's no work. Masses aren't being raised or lowered, so work is equal to 0. And you can factor that in when going through all of your processes. You'll know that work is equal to 0, so delta U is equal to the heat, and so forth. To succeed at this part of class, you're going to want to do many practice problems, and hopefully we're going to be able to devote the entire class period for this lecture to working through practice problems and getting a handle on how we want to do these things. And the practice problems in the back of the chapter will also be of much help to you guys. You can go through, check those out, and then you can check your answers with me. I don't think there's answers available in the back of the book, but it's a great practice to go through and figure out these problems. I'll also post some practice problems that you can do, and I'll give the answers to some of those as well, so you can check your work. And this is going to be a great way to familiarize yourself with all of these concepts, because at the end of the day, the math really isn't that hard. So if you have a really good understanding of what we're doing and what kind of equation we need to use and why we need to use different kind of equation and why the reversible work is different than the irreversible work, you're going to be able to put these things together and get the correct answers with relative ease. At this point, it's probably a little fuzzy, and it will be challenging for you until you familiarize yourself with these concepts. That's what you're going to want to be able to do in the next week or so, is really familiarize yourself with these various concepts. In the next couple of lectures, we're going to go through some of the same sorts of material, but we're not going to assume that we have an ideal gas. And so the notation will get a little bit crazy unless you have a lot of math background. So we'll go through and talk about what we mean, why we're doing the things we're doing, and develop some expressions that will allow us to solve for these functions here for non-ideal gases. To conclude, the internal energy of an isolated system is constant. That's our first law of thermodynamics. When our system changes energy, the only way it can do that is by gaining or losing heat or work. So either work comes out of the system or goes into the system, or heat comes out of the system or goes into the system. Heat and work are path functions that are dependent on the actual expansion or compression process that happens, while internal energy and enthalpy and the other various functions we'll look at are state functions that only depend on the initial state and the final states. If we understand these concepts, we can calculate the internal energy, enthalpy, work, and heat for any process for an ideal gas using our ideal gas law and the various equations that we've developed that also use the ideal gas law. So hopefully we'll have lots of time to go through all the questions you guys likely have in class and do a whole bunch of practice problems to solidify these concepts in our minds.